point in region 3. So what does it really looks like? Usually it looks like this, is that you have a positive and a negative, and then the electric field, we already know that the electric field point this way and the electric field point this way. And then, let's say this is more charges. Then we say there's a neutral point on the region 3. So therefore, there will be electric field line going this way, and then this part will have no electric field, and then the electric field will just go the other way.
Is there any situation where, because the conclusion for this type of question would be that the neutral point lies closer to the weaker point charge, is there any scenario that it does not happen that way?
First of all, I think it's good you identify that the neutral point should be closer to the weaker charge. It's maybe something worth memorizing for the examination purpose. But is there any possibility that this is not true? I think for the case of you have two positive charge, then the only possibility that you can have neutral point is the cancellation of the two electric field. And this is the math. Therefore, from what we did here, I think it is quite universally true. It's generally true that the neutral point will be closer to the weaker charge. I think there's no counterexample. You can see the math. You can also work out the case that when Q1 is smaller, then you will find out that the neutral point is closer to the in the region 1. But if you have free charges, of course, that is not the same. If you have free charges, then you do not just have the cancellation of the two electric field, you need to consider free electric fields in total. I remember this one they asked a lot in the DS in paper 1 about the neutral point. They do not call it neutral point, they just call it as a point where the electric field is 0. But I think a good remark is, I never think about it this way. I never memorize it, but I think in examination it would be good to know, is that for the case of, maybe I just remark in this way, that if you have, let's say, two positive charge, and then you have two negative charge, then you will have the neutral point located at the somewhere here. There will be neutral point. If the two charges are the same, then it's at the middle. But if the two charges are not the same, then you need to find it out. It will be closer to which one? If the two charges are if the two charges are positive, then the neutral point is closer to the one weaker. In here, you see, Q2 is smaller, so the neutral point is closer to Q2. Q2 is smaller, so the neutral point is closer to Q2. Yes. So for this one here, then the neutral points will be closer to the weaker charge. Somewhere between. Well, if the two charges are not the same sign, then in general we don't know which part is it, but it will be always located to the one with the weaker charge. So for example like this, then the neutral point will be located here because this is weaker. So therefore, the neutral point should be somewhere here. And then this is weaker. So the neutral point is somewhere here. Yes. Now, so therefore, neutral point about electric field, there's many things you can talk about. But for the neutral point of magnetic field, which is usually, maybe the neutral point of the gravitational field is the same first. For gravitational field, because the formula is so similar, gravitational field, we have G equals to Gm over R squared, but we don't have charge, we don't have positive mass and negative mass. The mass is always positive. So the field lines will always be pointing towards the mass. So it will be same in this case that this must be the region where I have the neutral point. Region where neutral point is located. So let's say the lowercase m is smaller. Based on like the conclusion we make here, that the neutral point should be closer to a weaker charge. For the case of gravitational field, where should be the neutral point? Should be closer to the larger mass or smaller mass? Kieran? Can we not using this formula, just using the observation we did here? In the case of electrostatic, weaker charge. In the case of gravitation, we refer to a smaller mass. Yeah. So if we choose not to use G equals to Gm over R squared to deduce it, then you should expect that the neutral point G equals to 0 closer to M, the one with a smaller mass. Well, if you want to verify, then of course just use Gm over x square, this is x1, equals to Gm over x2 square, and this is the lowercase m. Doing some algebra, you will see that x1 square over x2 square is equals to m over m. And since capital M, the uppercase M is bigger than the lowercase m, then we have x1 is bigger than x2. Therefore, x2 is smaller. So therefore, you are having the neutral point should be closer to the smaller mass. Sorry, this is 2. So it's the same math here. This equation, Gm over R squared, the cancellation of 2 Gm over R squared, and the cancellation of the 2 Q over 4 pi R squared is the same math. So therefore, for the finding the neutral point, they should give me the same. The electrostatic is more difficult because electrostatic, you can have a case that one charge is positive, one charge is negative. But it turns out that although the region where you can find neutral point is different, it will have to be on two sides, on both sides, or either side of the whole system, instead of between the two charges. But the result is the same. The neutral point is located near to the charge has a smaller magnetic field. Interesting. But for magnetism, we can still talk about neutral point, but at least not for the bar, at least not just for one bar magnet. If for magnetism, you just have one bar magnet, then everywhere near to this bar magnet should have magnetic field. And when you try to make it symmetric, also remember to start the beginning of the field lines on the bar magnet. I don't know why some students when they draw, they draw something like this. This is actually not good. You should have a starting point of the field lines. Also, don't draw something like this. This is also not okay, because you should not have the field lines to touch each other even on the surface of the magnet. This is not what we expect to see. So the field lines go like this, and then this one goes to here, this one goes to here, and the same on the other side. So the density of the field lines tells you how strong the field is. So therefore, here, high density, so therefore the field is high. Here, the density is lower, so therefore you have a smaller B field and lower magnetic field. But no matter how, there's no neutral point here, because there's no way of cancellation. There's only one B field. The only way you can have a cancellation will be having two bar magnets. You have two bar magnets, then you have one north pole, maybe another one is a north pole as well. Then, because this north pole will try to produce a magnetic field this way, and then this north pole will try to produce a magnetic field this way. So therefore, at this location here, there's a chance you find a place there is no magnetic field, because the two fields are identical and then the two fields cancel each other. Well, how about not bar magnet? How about current? If you have currents, a straight wire has a magnetic field. So the formula is B equals to mu naught I over 2 pi r. So if you're interested to find the magnetic field here, let's say this point, at a distance r from a current, then the magnetic field strength at this point will be given by this formula. B equals to mu naught I over 2 pi r. This is the magnitude. How about direction? Putting into the paper, just using the right hand grip rule, that the thumb of your finger, the thumb of your hand is the current, while the four fingers will be the direction of the magnetic field. So therefore, on the right hand side of the currents, the magnetic field is going, I'm not drawing the right finger. Let's see, right hand, yes. No, right hand, like this. That the right hand, and then this is the four fingers. So the four fingers is in the direction of magnetic field. Therefore, on one side of the currents, the magnetic field is going out of the page. On the other side of the current, the magnetic field is going into the page. So therefore, in principle, you should say, oh, there is a magnetic field, magnetic field, magnetic field, magnetic field, all in all the region here. And there's a magnetic field going out of the page, magnetic field go out of the page, magnetic field go out of the page. spreading out on both sides of the current. And then the direction is determined by the right-hand grip rule, while the magnitude is given by mu naught I over 2 by R. So again, if you have just one current, there's no way you can have neutral points. But you have two currents, then that is possible. Now let's see, can I conclude that if you have two currents, then the neutral point is closer to the one with a smaller current? I think maybe. Let's say in this case, you have two currents. I call it I1 and I2. So I denote this, let's say this is in red. On the right-hand side of this current, what is the direction of the magnetic field? On the right-hand side of the current. Here. Okay, you use the right-hand grip rule. So go around. On the right-hand side, it should be going into the paper. I don't know. I2 may not be equal to I1, but it's going out of the page and then here. How about here? Also into. So as long as it's on the right-hand side of the currents, I1 here, the current is going up, then the magnetic field will be pointing into the paper on the right-hand side. Then for I2, then let's say this time I have the current going down. Then I use the right-hand grip rule. Then the current is going down. So I will have the magnetic field going out of the page on the right-hand side of the current, and then going into the page. So therefore, you see in this case, only these two regions that you can have neutral points. So it's possible, because the two magnetic fields are in opposite direction, but in this region, this is impossible to have the neutral points. Then the next question is, okay, then which region is it? So we need to have I1 bigger than I2, suppose. Then for the usual practice is that, okay, then I will have B1 equals to B2, and then B1 is equals to I or mu naught I1 over 2 pi R1, and then B2 is mu naught I2 over 2 pi R2. And then therefore R1 to cancel mu, cancel 2 pi. Then I will have R1 over R2 equals to I1 over I2. So if I1 is bigger, then R1 will be bigger. Or maybe I2 is smaller, then R2 is smaller. If R2 is smaller, then that means it is closer to R2. So it means closer to I2. Hence, smaller current in this case, then I have the neutral points located on the right-hand side of the whole system, and it is closer to the current of a smaller size. So that means it's a good result. It means that it's the same as before. Just like before, here, or we did the calculation here before. We think that if the two charges are opposite or are of opposite sign, then the neutral point will be on either side of the system, not at the middle, but which side? Well, it will be the side closer to the weaker charge. Then the same thing happened this one. If the two current, well, current does not have positive and negative, but the current has directions. If the two currents are in opposite direction, then it means that you have the neutral points located on either sides of the system, not in the middle, but the neutral points will be closer to the current with a smaller size, with a smaller current. So therefore, the result is this one. So then we still apply. We can immediately try to check what if the two currents are in the same direction. This is something like two charges, like this. And let's say, oh, one charge is more positive. That means it's like this current is larger. Smaller. Then this one is smaller current. For the case of electrostatic, where is the neutral point? In this case, closer to which charge? To the smaller charge, and is in the middle. So therefore, the neutral point should be here. Somewhere closer to the weaker charge. Closer to weaker charge. So we should also expect here that this is the neutral point and it is closer to the smaller current. Yeah. So it's quite universal. I think it's a very good, I think when we mean to memorize something, we try to memorize something that apply to all cases. Well, for the case of you have free currents, then I think it's beyond what we can do. Free currents, would that be in DSC? Free currents. And then find neutral point. We have seen system of free currents. But usually they will ask about what is the force on one of the currents instead of finding neutral point.
For force is very easy. If they are in the same direction, then it's attractive. And if it's
Yes. That one is also a useful thing to memorize, okay? Like this one here. That if let's say we're not talking about neutral point anymore, we just talk about the forces between the two currents, then it will be like this. How do we memorize it? I would think it's just opposite to charges. For charges, you have positive and negative. We all know it will attract, like from day one. Positive, repel positive. And then negative, repel negative. And if you have positive and negative, then they attract. But for the case of current, it's opposite. If the two currents are the same, then they attract. If the two currents are opposite, then they will repel. You can memorize in this way. Sometimes it will really help you to solve some multiple choice question. Another way to memorize it is if the two currents flowing in the same direction they repel, then you can never really have electric circuit. Because instead, in the electric circuit, if you have a wire, inside the wire, the current are flowing in one direction. But why you can say there's only one current? You can say this one single current is made of many, many currents. Let's say 3 amperes. 3 amperes, you can say that's actually composed of 1 amperes plus 1 amperes plus 1 amperes. If in the world that we have the currents flowing in the same direction, they will repel, they will not flow in one single wire, then you cannot have electric circuit to use. So, yeah, if that is the case, if the two currents in the same direction, they repel, then even on a single copper wire, you have infinite resistance. You can't have current to flow anymore. So, you can understand that way. Anyway, so many different ways to understand. I think for multiple choice question, being able to record this result is helpful. But for explanation, of course, we better also need to know. Did I mention that last time? Why is it upside down? No, here. Oh no, I did not explain it in the video last time. I just explained to a student, I don't know when. That the Fleming-Stephan rule for two currents. Just cover a bit, just in case you really know. So we say the Fleming-Stephan rule has the thumb, index finger, middle finger, and then we're saying that this is the force. I did not talk about that. There's a force, and there's a magnetic field, and there's a current. And we need to, when we apply this, for one current, it's usually okay. But you have two currents, then not everyone apply it easily. For example, I have I have one current which is IP, and then other current which is called IQ. IQ is going into the page, IP is going out of the page. And then and then that's it. They are not in any magnetic field. And then in this case, they may ask, okay, then what is the direction of the force on IQ? If you memorize the rule, you can say, oh, so simple lah, because the two currents are in opposite direction. So if they were charges, then they will opposite charge, they will attract. But Mr. Wong said it's the opposite to electric charges, so they should try to repel. So therefore, the force should be going this way. But can you explain it using Fermi-Stephan rule? That is the question. I think some of you know already. So I think I talked about it. Donald, did I talk about it? Yeah. Here, right, in this room. But why I can't find it? I don't know where is it. Then Donald, can you explain it?
Okay, so you use the left hand rule.
Yes.
And then after that you use the right hand rule.
Yes.
And boom. No way, you use right hand rule and then left hand rule.
Left hand rule. The thing
right
is
hand, right hand rule first and then left hand rule.
Okay, yeah. But let me go this way. Left hand rule first, I say left hand rule, you want to find the force, and the force is on IQ. So therefore, you use the left hand rule at this location.
Right
so here, you know FBI, I know the current. The current is going into the page here. But I need to know what is the direction of the magnetic field. If the magnetic field is going up, I know the force is going this way. If the magnetic field is going to the right, then the force is going down. So I need to know the magnetic field here. But how do I know the magnetic field here? Then you start to use right-hand rule. You use right-hand rule, or I use right-hand rule, and then I know that this is current, this is magnetic field, then I put it here. Well, then the problem is, if you use the right-hand rule, on the right-hand side, then you will find the magnetic field is going in the clockwise sense. But this is not what we want. This only tells you where's the magnetic field here, or the other places. But it does not tell you what is the magnetic field at this point. Use the right-hand rule can only tell you the magnetic field around the current, but not at the current. So therefore, not useful. So I need to use the right-hand rule at this IP. And if I do that, then I will have the magnetic field going in the anti-clockwise sense. And therefore, if you extend the line, therefore, using the right-hand rule at this point, it will tell me the magnetic field at this point. And this is what we want, because left hand, I want to use the Fleming's left-hand rule here. I want to know what is the current exactly at this. I want to know the current exactly at this point. I want to know the magnetic field exactly at this point. Then I find out, because the current exactly at this point is going into the page. The magnetic field is exactly at this point is going up due to this current. So therefore, I can conclude that the force is going to the right hand side. So you use the Fermi's left-hand rule here, but you use the right-hand rule here. Because it's nothing wrong to apply right-hand rule here, but it does not tell you the magnetic field at this point. It only tells you the magnetic field around. So that's why you need to apply the right-hand rule here. Yeah.咩 question？ 呢啲或者即係話 forcing， 係咯 ，just how to。你講唔完啊！你有咩問題啊？If you have any question, they jump to that.
This is two solenoids.
Two solenoid.
Yeah, inside of each other, right? And then this
Oh.
one government, right? Because it's like this, so this one's north, this one's south, and this one north, south. And then it asks for this point is point P. Why do I not consider the magnetic field of this thing, like the magnetic field line of this? Only consider the.
Oh, okay, yes. This one is a magnetic field. Let me frame this into like a section. Magnetic field due to a solenoid. I think this is about a kind of convention is that, first of all, we need to understand about one solenoid first. So a solenoid is like this. If you, let's say the current flow like this, so the current is flowing down on the side of the solenoid closer to us. If we don't want to, this is good enough already, but sometimes I would even practice my drawing. I will draw something like this. Okay, this is what it means when you do cross section. The current is going into the page at the bottom part of the solenoid, and the current is going out of the page at the upper part of the solenoid. So you got this. And use the right-hand grip rule, then we can deduce that there is a magnetic field going out this way. And then, like this. So we say that, oh, this looks so much like a bar magnet. That is also the reason why we call solenoid can be used to make electromagnet, because it looks so much like a bar magnet. as the pattern of the electric field. To zoom inside, what you see is actually you have a few lines that are parallel to each other. And then I can't draw it well, like this one here. There's also a few lines here. And there's also a few lines here. Like this. Okay. So the interesting part here we want to mention about it is that there's a uniform field here. Then you may say, hey, it's not uniform because you see this part, they are not parallel. When you get closer to the end, the field lines are not parallel. Yes. However, when you are going deep inside the solenoid, around this part, which is deep inside the solenoid, we claim that it's a uniform field. Well, uniform field is constant, so therefore we can write down a formula for that. And then the formula for that uniform field is in your equation book, is B equals to mu naught N over L times I, where L is the length of the solenoid, and N is the number of turns, and mu is the constant. In the equation book, I is the current. But you need to always remember, we can only use this equation deep inside a solenoid. In other words, we are saying that we are using this formula only for the case that the solenoid is long enough. If the solenoid is really small, then there's no way to talk about uniform field inside. Only when the solenoid is infinitely long, then we can talk about the magnetic field inside being constant. So therefore, this is only true or based on the assumption that the solenoid is long enough, a long solenoid. Well, however, if the solenoid we consider is long, then the magnetic field outside will have to be very weak, because I can connect from here to here because this part is, and then this part is still closer to the solenoid. But if this one is infinitely long, then this one may need to go very, very far away and then come back. So in this sense, when you have the solenoid get longer and longer, the field here on outside of the solenoid will get weaker and weaker. If the solenoid is infinitely long, then these two will be zero. So when you have this assumption, the field outside will be zero for a long solenoid. Well, you may say, think about it first. I'll organize it later. But therefore, you don't need to consider. Therefore, when you have considered solenoid, then you in our model only inside you have a magnetic field given by this formula. But if you are talking about outside, then the magnetic field will be taken as zero. Taken as zero because we are using this assumption. Did I confuse? Lamasi.
Then is there, do we need to know the explanation why at the size of the solenoid, the B field is basically E over 2? So 1/2.
No need. No need. You don't need. I didn't recall that it appears in the DSA exam, but you kind of need to know that inside the solenoid is this one. But when you get closer and then we go to two ends, the B should drops. But there must be a place that you drop to B over 2. Because you go further away, then the B goes to 0. then with some place that is B over 2.
So why we need to find the B field per length?
Huh?
Why we need to find the B field per length?
Why I need to find a B field per length? No, we do not find B field per length. We find force per length. This equation?
B, y dash over L.
Oh, y dash over L. Well, it is. Well, then you ask about how we derive this formula. This is not something we could do. But as you ask about this n over L is usually represented as a lowercase n, which means the number of turns per unit length.
Okay.
This one is sometimes written as mu naught ni. This I will be, this n will be capital N over L. That means it is just the number of turns per unit length. So therefore, it's not to say, well, you have more turns, therefore you must have a stronger magnetic field inside. It's not true. Because you have more turns, maybe you have also longer the solenoid. So by widening more turns on the solenoid, but the number of turns per unit length remains unchanged, then the magnetic field inside should remain unchanged. The only thing you can say is when you have a longer solenoid, then the B field inside will be more uniform. I think when we are using this equation, we already have assumed that you have a very long solenoid. So have a very long solenoid and you keep widening more turns, it should not change the magnetic field if it have still N over L the same. Think about this, we call an example that let's say you have a solenoid that is a bigger solenoid. And then this one has N1, N1 and then L1. And then you have another solenoid that is inside the first solenoid. But the current, and then you got current flowing in, and then the number of turns inside is N2 and then L2. And then you pass the current to I1 here. And then on the other side, you have current I2, but it's in opposite direction. Then we can actually ask, what is the, let's say here, what is the magnetic field here? So since the currents are in opposite direction, the two magnetic field, or what is the direction of the magnetic field at the point in red?
From left to right.
To the right. Yes, I use the right hand grip rule. Then the magnetic field due to the current in black will be to the right. And then using the right hand grip rule, then the magnetic field due to the current in blue is to the left. But they may not be the same. All we know is just they're in opposite direction. Therefore, it will be equals to B1 minus B2, and then it is equals to mu naught N1 over L1 I1 minus mu naught N2 over L2 I2. Like this. Still, we can have cancellation. we can have neutral, we can have zero magnetic field inside the solenoid in this point right here. If you have, let's say, neutral point, if B is 0, then I will have B1 equals to B0, B2, and in order for me to have that means I need to have N1 over L1, I1 equals to N2 over L2, I2. The question may tell you that, oh, maybe, I don't know, maybe I1 equals to I2. Let's say, maybe, we're doing something like this. We are actually form a circle like this. In the past, I can't say, oh, this is so much unlike DSE paper. This is so much that the people will do in the tuition center. They think, and then try to make a very, very difficult question to how to say, to destroy your confidence so that you pay more money to buy the lesson. But as I kind of mentioned in the class, is that this last year, the DSE chief officer has retired, so they changed the person. So therefore, the style of the question. So in the past, that person called not Isaac, Cito, and then he has been the chief examiner for so many years, since the day when I was still a student. So and then, but he retired already last year. Therefore, we have a new young chief examiner, and then well, we don't know much about him, but at least we, as a teacher, I found out that the style of the question changed, obviously has changed, and therefore maybe that is also still possible. But anyway, no harms to know more things. Then, so let's say I got something like this, and then I just study the case that I have B equal to 0. How would that be possible? It will be possible if, so I1 equals to I2, because it's the same circuit. So therefore, the ratio of the number of turns, not the ratio, the number of turns N1 over L1 must be equal to the same ratio. In this drawing, L2 is smaller. So therefore, L2 is smaller. So therefore, we got N2 over N1. If L2 is smaller, L2 is smaller than L1, therefore the number of turns. Did I do something wrong? Since the L2 is shorter, and therefore the number of turns in the coil in blue should also be smaller. Some people will say, oh, okay, you want to have cancellation inside, then the one in the magnetic, you want to have cancellation inside, so therefore you need to have more turns inside. But actually not true, you don't have to. All I need is, you just need the ratio of the turn to the length. That means the number of turns per unit need to be the same. You have the coil, the solenoid in black, is longer, of course it has more turn. But all I need is just the ratio of the number of turns to the length to be the same. Therefore, when you have another coil, which is inside the first solenoid, and it is shorter, then naturally, you just need to have a smaller number of turns. Because you should remain the ratio the same. You don't need to say, oh, this is shorter. In order to cancel the B field, then must be it has to have more turns. The cancel one, no need. You just need the ratio. In this case, my current is uniform. So therefore, yes, I was thinking that, therefore, for example, let's say when I have a solenoid going in this direction, and then you have another solenoid that the current is going in opposite direction, and then if we suppose that they have the same currents, and then they have the same number of turns per unit length, if you have two solenoid like this, then this region will have no magnetic field. B will be 0. And only this part has magnetic. And what will be the direction of the magnetic field? In this region, which is the right-hand grid rule, going like this, so the ring outside will produce a magnetic field going into the page. This into the page. And this one will produce a magnetic field going out of the page. But only this part. So the two field cancel. Outside this smaller solenoid, in this region, it will not experience any magnetic field due to the small solenoid, because we say that we will say that B is equal to 0 when it is outside the long solenoid. So therefore, this part here will have the magnetic field going into the page. Okay, the explanation is because this one produce fields into the page and no field outside, and then the smaller one produce a magnetic field out of the page, and then B field outside is 0, and then we say that this part cancel the field here. This is so ugly. Let me remove this. So produce a B field here like this. So these two B field cancel. So therefore, there's no B field inside the smaller solenoid. How about magnetic flux? This setup also reminds me about the magnetic flux. Do they have the same magnetic flux? I think they ask about, it's like they produce a magnetic field and this is the current, and then you have another solenoid. This is inside. But this solenoid is not have any magnetic current. So this solenoid is, maybe I don't even need to draw this part. Like this. So you got another solenoid. So what is how to find the magnetic flux linkage of this small solenoid? So of course you are given a current I, you are given, let's say, the diameter of the solenoid outside, you have the number of turns of the first solenoid, you have the number of the length of the solenoid, you also have the diameter. I just call this the bigger diameter. Let's just call this R. So we call this R, and then we call this this is like the SS, and then call this small r. And then I call this N. The number of turn here is N. Call this N, maybe. Then what is the magnetic flux linkage? It's called N1, N2. Magnetic flux linkage.
Yeah, being over L.
入邊嗰個冇所謂咯，其實。The one inside, I can call it L2. But what would be the expression for the magnetic flux linkage? BA, MBA. Which N? For the ring, for the solenoid inside, for the small solenoid.
Inside the small solenoid. Situation time.
Yeah, the magnetic flux linkage of the small solenoid inside the big solenoid.
And B1 now B2.
No. Why B1 plus B2? There's no current in the solenoid. Let's call it solenoid 1 and solenoid 2. There is no current in solenoid 2.
Oh, N1, B1, A1. A1 is I, R squared.
And this N should be the number of turns of the solenoid. And we are talking about the solenoid 2, so therefore it's N2. And B should be the magnetic field experienced by the solenoid. And you have the only magnetic field here is produced by the current in the big solenoid. So therefore, it will be going. It will be B equals to mu naught I over. No, not mu naught. It should be mu naught N1 over L1 times I.
First one.
It should be B, right? Because the magnetic field produced by the solenoid 1 is mu naught N1 over L1 times I1 times I. And then A should be the area of the solenoid.
Oh, solenoid 2, right?
Solenoid 2, yes. Area of solenoid. So therefore it's pi R squared. And this is the magnetic flux linkage. So therefore, you see the magnetic flux linkage. Let's say this is phi 1, phi 2. This phi 2 is proportional to I. So therefore, let's say the current changes with time. Then what will happen to the magnetic flux linkage? It will also change with time. But if the magnetic flux linkage changes with time, then you have EMF induced. We can study this for EM induction. Because just recall EM induction. Always say that is the magnetic flux changes with time. Then the EMF induced is equal to minus the rate of change of the magnetic flux linkage. So if you, let's say if you have the I is an alternating current. I changes with time. Then, since we know the magnetic flux linkage is also proportional to I, so the same graph can be fine. Or maybe not exactly the same magnitude, but the same graph will be the same. Will be fine. Then, the Faraday's law tells you that the EMF is the negative of the rate of change of magnetic flux linkage. In other words, you look at the negative of the gradient. Then you will find the EMF. Okay, for example, let's say the gradient is positive here. So the negative of the gradient, so the EMF will be negative. So the
Why is it negative?
here?
Why is it negative?
Or this for this length is law, or you can just take it as part of the definition of the Faraday's law. Just in nature, this is negative. Then you got very positive at first, and you got 0, so you should get very negative at first, and it goes to 0. And then the gradient is and then the gradient becomes more and more negative. No, and you have more and more negative. So negative of it, that means it becomes more and more positive. So once you start the sketch, then you get to it very soon. Now let's take, for example, here, no EMF, here no EMF, it happens here and here. Because the gradient is 0, so there's no EMF. The gradient is 0 here, so there's no EMF.
How do we get a graph of the high order flux?
Oh no, this is not our flux, it's IT graph will look like this. The flux T graph will look like this. They're proportional, so they look exactly the same. We deduce it from.
Can I go up and see the whole of this? Oh,
You were not. NBA magnetic flux linkage. Anyway, we call it already. You can go home and then watch the video. But the magnetic flux linkage of 2 is number of turn of 2, so therefore N2. B field experienced by 2, that is the one produced by 1. So it's the mu naught M1 over L1I. And then the area of 2, so it's pi R squared. R is the radius. Everything constant here, no way to change the time except I. So the current flowing through can be changed with time. So let's suppose it's AC, then we can have EMF induced. Huh?
I find tomorrow.
Oh. What's time now? 36. Oh, wow. Oh, wow. We do a recap. I think it's quite exam oriented. The first is that we look at this part, which is about the neutral point. This is quite common in multiple choice, paper 1. And then the basic principle is, in order for you to have neutral point, you need the field lines to be in opposite direction and equal magnitude. So therefore, we will frequently use like the formula like electric field due to one charge equals to the electric field due to the second charge. So we set up the equation like this. And as it turns out, when we do this, based on the size of Q1 and Q2, we'll have different results. If the two charges are the same, of course it's so simple, the neutral points must be at the middle. But DSC will be not that simple. The Q may not be the same. And then we find out that with this mathematics here, the neutral point will always be closer to the smaller charge. It will always be the case. We did this analysis here, and then I summarize it here, that the neutral point, I don't know which charge is bigger, but let's say this is weaker, then the neutral point will be closer to it. If this is weaker, the neutral point will be closer to it. For the case when the two charges are the same sign, then it must be easy to reach. But if the two charges are not on the same sign, it must will be either this side or this side. Then which side? We just look at the case with the weaker charge. If this charge is weaker, the neutral point is closer to it. If this charge is weaker, the neutral point is closer to it, so must be here, not here. Because this one is spread out with the weaker charge. And it turns out that this idea can be applied to the case of gravitational force as well. You have a larger mass and smaller mass. Using all the math, we find out that the neutral points will be closer to the smaller mass. It will also be the case that if you're talking about currents, that when you have two currents like this, that they are of opposite currents, so the only place where you can have neutral point will be here or here, because the B field they are in opposite direction. And it turns out that using all the math, we find out that if the current 2 is smaller, then the neutral point will be here, because this part is closer to the weaker current. It won't be on this side. And the same thing even when the currents are in the same direction. If this is a weaker current, and they're in the same direction, so therefore the neutral point must be somewhere here in the middle. And it will be closer to the currents which is of smaller size. That these two are identical. Same current, same charge. Weaker charge, they will get the weaker points. So this is quite universal. And then after that, we look at this Fermi-Zappan rule things. I think it's very popular question in DSC. And just to remind you that you are using Fermi's second rule, yes, so you need to use it in the right way. We talk about the force here, then please find the current here and the B field here. To find the current here is obvious, you just look at the diagram. You want to find the magnetic field here, and you use the right hand rule, but not at this point. You use the right hand rule here, it only tells you the magnetic field other places, but not this point. So therefore, you want to find the magnetic field here, you should use the right hand rule on here. You do this, it tells you the magnetic field everywhere, including this point. So therefore, you can use your Fermi second rule. And last part is about the magnetic field due to solenoid. I think the key point is you recognize how to draw the pattern. Again, use the right hand rule again. Then you have the magnetic field going to the right. And then outside, we will take the magnetic field to be 0 for a non-solenoid. Inside, for a non-solenoid, we can take the magnetic field as this one. This is given in the equation book, that N over L, but you need to be aware that this question that I asked, because intuitively we may think more turns, larger N should have more field, but this is actually not true. What really matters in determining the magnetic field strength is the ratio of the turns, of the number of turns to the length of it. It's just a ratio. But usually when you put more turns, you're actually also increasing length as well. So therefore, if you just apply a few more turns, it actually increase N but increase L as well. So it will not increase the B. Unless you use thinner wire. So therefore you wire more number of turns in the same length of the solenoid, then you can have length constant, then you have the number of turns to increase. Then in this case you can increase the magnetic field. And after that we did some, I think, a little bit advanced or the application of this equation, that you have two solenoids. Then I try a bit to see, can we talk about neutral points? It turns out we can. This time we have two magnetic field, and then we can just equate the two, and then we get some formula. And then I try to simplify this formula by saying that, let's say the two solenoids are connected in series with a cell, so the current cancel, the current are the same. So you get a formula like this. And it will, in this case, then we can have the neutral point inside the solenoid. But I don't think, this time you need to go home and watch the video one more time. It's a little bit too abstract for some of you. And then, yeah, this is like the another example, which is, I think is also a little bit abstract. But I think now I cannot say it won't happen in DSD anymore, because from the last year I look at the question, the style of the question is quite different. So it's possible that it can appear in Excel.
Sir, you mean magnetic flux equals to NBA?
Magnetic flux equals to NBA. Yes, magnetic flux is defined, flux linkage is defined as NBA.
What's flux linkage?
Flux is BA. Flux linkage is NBA. You just multiply N to a flux, then you get a flux linkage.
So actually induced EMF equals to flux linkage over delta T?
No, not flux linkage over delta T, but it's flux linkage, but it's change in flux linkage over delta T.
Oh.
So it's a change. That's why you need to look at the slope. If you're not, we actually.
Is flux 2 the bigger solenoid?
No, flux 2 is, in this example, flux 2 is the smaller solenoid.
Smaller solenoid equal to solenoid times bigger solenoid. Oh, that makes sense.
In this example, the bigger solenoid is 1. The current flow in the bigger solenoid,
Okay.
producing a magnetic field. And then the smaller solenoid, solenoid 2, is inside the big solenoid. And this second solenoid, solenoid 2, experiences the magnetic field. So it has magnetic flux linkage.
I'll get the graph again, like the on the left hand side.
On the left hand side is given.
Oh, given?
Suppose the current changes with time.
Oh, okay.
Then how will the EMF induce?
Okay.
I think the part about graph we finish here. And then